Hi there, welcome to the subject of UEME 3133 Mechanics of Machines. So today, in this great evening, we have gathered a group of 6 mechanical students to talk about the multi-cylinder engine. So as a science student, we are always curious on how things work. So let's not wait and proceed to the details. Hi, I'm Wong Kim Fei, and I'm going to talk about the multi-cylinder engines. As we have learned the design of slider crank mechanism for the single-cylinder internal combustion engine, now we're going to apply the same idea on multi-cylinder engines. So in the industry, there are few types of engines such as inline engines, V engines, opposed engine, radial and rotary engines. Each of these designs will have their own characteristics. So let's have a look on their design. So inline engines, from the appearance itself, the cylinder is arranged in a row in an axial direction. So the commonly used of cylinder numbers is 2, 3, 4, 5 or 6. Besides that, from this animation of the inline engines, this part of the cylinder is the crankshaft of cylinder 1, and this is the crankshaft of the cylinder 2. So the crankshaft of cylinder 1 and the crankshaft of cylinder 2 will have an angle of 180 degrees, and this angle is known as the phase angle. So this phase angle will give a significant effect to the firing order of the engine itself, which is contribute to the dynamic action of the engines, the performance of the engines. Next, it will be the opposed engines. As we can see that opposed engines can be seen as two inline engines merged together at an angle of 180 degrees from each other, and with a center merged up with a common crankshaft. So in this opposed engine design, there has a benefit of the cancellation of inertial force. So let's have a look on the animations. The first cylinder is having a compression, and the second cylinder is also having a compression at the same time. So when two compressions happening at the same time, the inertia will cancel off on each other. So that's why this design will have a cancellation of inertial force. Next, it will be the radial and rotary engines. So radial and rotary engine are having a different design as compared to the inline engine and the opposed engine, because previously in the inline engine and opposed engine, the cylinder are arranged in axial directions, but in radial and rotary engines, the cylinder are arranged in axial directions, which is in the same plane. So and this design of the radial and rotary will give the engine itself have a good cooling system, because each of the cylinder will have a high exposure of area to the air. That's why it can cool better than the better than the inline and opposed engines. Besides that, there are difference between radial and rotary engines. The difference is radial engines will have a moving or rotating crankshaft, but the crankcase and the cylinder but the cylinder case and the cylinder itself is not moving in rotational motions. Okay, as from rotary, the cylinder and the cylinder case are moving in rotational motions. However, the crank itself is in stationary. That is the difference between radial and rotary engines. Next, it will be V engines. V engine also can be seen as two inline engines are merged together at a certain angle, such as 60° or 120°, and this angle is known as V angle. If the V angle is 180°, it will be known as the opposed engine, as we have discussed earlier. So the two inline engines of this are merged together and joined by a common crankshaft in the middle. Usually the design will have 2, 4, 6, 8 or 12 cylinders. It will use as the design for V engines. And then the choice of the V angle and the choice of the phase angle, which is the angle between the crank throw, will have a significant effect on the dynamic condition on the engine, such as the shaking force, the initial torque, the shaking moment, and the even firing. And this is an example of V6. And now I'm going to pass the remaining part or the next part to my friend Ziming.
My name is Ng Ziming. Now I'm going to explain about the crank phase diagram of a V12 cylinder engine. First of all, we must find the phase angle and the crank angle. Phase angle is the angle of each cylinder with respect to the first cylinder. Usually the first cylinder is used as the reference point. To obtain phase angle, we calculate by 360 divided by n, where n is the number of cylinders. In our case, we are using 30° as the phase angle. Next, the crank angle is the angle of rotation of a crankshaft measured from the top dead center, where piston is at the highest point. The crank angle will be 60°. There are many possibility angle that can be used depending on our engine design. So the selected phase angle and crank angle by us might not be the ideal case. Further calculation is needed to determine which angle is ideal. The diagram shows the arrangement of 12 cylinder engines, where L is the left side and R is the right side of the engine. In V12 cylinder engine, there will be two crankshafts. Now I'm showing the first crankshaft revolution and the second crankshaft revolution of our V12 cylinder engine. Next, as selected, the phase angle will be 30°. If we rotate counterclockwise, it will be a negative angle, while clockwise it will be a positive angle. From graph, at the peak, it represents the cylinder largest velocity magnitude. There are 12 cylinders, so there will be a 12 graph. Now I will talk about the shaking force. Shaking force is defined as the resultant of all forces acting on the body of engine due to inertial forces. For a multi-cylinder engine of 12 cylinders, we can use the following formula. Shaking force will contribute to the unbalance of the motor or engine. So the ideal value for the shaking force will be 0. This expression can only be 0 for all the values as shown is equal to 0. We will add some extra mass or reduce the mass or add extra component to balance up the shaking force. Thank you.
Hi, I'm Andy Tian. I would like to present my topic of inertial torque and the shaking moment of our V12 engine design. Inertial moment is due to the motion of the piston, which is acting on the point where the connecting rod and the crankshaft is connected. It can be represented with an equation which is shown in the slide. The Ti is the inertial torque, M is the mass of the piston, R is the length of the crankshaft and also the radius of the rotating path. Omega is the angular velocity of the rotating crankshaft. L is the length of the connecting rod, and then the theta is the crank angle, which is measured from the vertical axis to the position where the crankshaft is. By using this equation, you can plot the graph of torque versus the crank angle, and it is plotted with the range of 0 to 720 degree. Now this picture shows one of the piston in our design V12 engine. The yellow arrow means the direction of the piston moving, and then the green arrow is the point where the inertial torque is acting on. The red arrow is showing the direction of the crankshaft moving. The blue oval shape show the balancing weight, which is used to counterbalance the inertial torque. The balancing weight has the same radius from the point of rotating, and it has the same mass as the inertial torque, so that both of them has the same magnitude of torque, but in opposite direction, so they can counterbalance each other. Now is the shaking moment. Shaking moment is also due to the motion of the piston. However, it is due to the overall pistons, which is different to the inertial torque. Inertial torque is only due to a single piston motion. So the shaking moment is the shaking of the whole crankshaft. This can be understand more by referring to the blue arrow as shown in the slide. Inside the slide we have green arrow, which indicate the upwards motion of the piston, and then the purple arrows which indicates the downwards motion of the pistons. Now we're taking the moment in the middle of the crankshaft, then we can counterbalance each force produced by the piston, so the overall shaking moment of this crankshaft is equal to 0. This ideal speaking theoretically, however in reality we still have some shaking moment due to some imbalance of the error of producing the piston. Now this all of my present, so I pass to my next friend.
Hi guys, My name is Yi Xian, and now I'm going to present to you a topic which is about even firing on V12 engine. First of all, what is even firing? From the name itself, we can understand that it is firing done evenly. In more technical words, it is power pulses evenly spaced in time. But how much is it spaced? That will depend on the number of strokes and also the number of cylinders. Since our product is a 4-strokes V12 engine, so to calculate that, we calculate a value called delta phase angle, which is this one. So in order to calculate the value, we substitute n equals to 12 into the equation, and we get the delta phase angle equals to 60 degree. And this 60 degree is where the power pulses are spaced from each other. Next, let's have a look on the video. Here, we can see that the power pulse is done at a time interval between each other, and it is running from one cylinder to another in a cycle. Next, let's look at the crank phase diagram of V12. Since V engines are arranged to fire cylinders in opposite banks successively to balance fluid flow demands, so we can see that at the right bank, this diagram shows the right bank, the cylinder 1 fires first at a crank angle of 0 degrees. Then it is followed by the left bank, the first cylinder in left bank, which is cylinder 7, and we can see that the power pulse is fired at the angle of 60 degrees. Then it is followed by right bank, second cylinder, which is cylinder 2, which fires at the angle of 120 degrees, and so on. And we can notice here that the power pulse is spaced by 60 degrees between each other. And this arrangement is only an example. There are actually many different ways of sequencing the firing order of the cylinders. And in order to balance the V12 engine, inertial torque and shaking moment needs to be taken into account. But here, for simplicity, we simply ignore them. That's all for my part, and now I'll pass to Jeffrey to continue.
Hello, I'm Jeffrey, and today I'm going to talk about the balancing of multi-cylinder engines, which are divided into 3 subtopics, which are the rotating masses, the unbalanced inertial force, and also the reciprocating unbalanced multi-cylinder engine. For the rotating mass unbalance, there are basically 2 types of balancing, which are the static and also the dynamic balancing. For the static balancing, if it can be placed in any angular orientation and not roll on the knife edges, it is said to be static balance. And as for the dynamic balancing, it can be achieved by using of counterweights installed opposite of each crank throw. The figure below shows us how the dynamic balancing works. Then I'm going to talk about the unbalanced inertial torque. It can be smoothed with a flywheel for the single cylinder engine, and the function of the flywheel is to smooth its variation in gas torque even it has 0 initial torque. The figure below shows where the flywheel is positioned in the crankshaft. And finally, I'm going to talk about the reciprocating unbalanced multi-cylinder engine. There are basically 2 types, the incline 4 engine and also incline 6 engine, which we are going to compare as below. The incline 4 engine has primary and secondary components. where the primary components require two balance shafts rotating at crank speed, one of which can be the crankshaft itself to cancel it off, while for the secondary component, it usually requires at least two balance shafts rotating at twice crank speed, gear or chain drive from the crankshaft to cancel it. The secondary component can be solved by using the Lanchester balance and Nakamura balance. As for the inline 6 engine, which is used in our assignment, it is perfectly primary and secondary mechanical balance without the use of a balance shaft. This is because the crankshaft has 6 crank throws arranged in 3 planes offset at 120 degrees.
After this presentation, I hope that you guys will gain more knowledge about this cylinder. Thank you.
우연히 내게 다가와 감싸 안아주고